Hello and welcome to yet another video of Cornerstones of Math. A sequence AN is defined by the recurrence relation. A1 is 1/2 and AN plus 1 is given as 2 over 3 minus AN for all natural numbers n. Find the limit of AN as n approaches infinity. First, I will show you several non-rigorous methods. That is, although these methods may provide the correct answer, their logics are not 100% mathematically strict. First, from the given recurrence relation, let us think about the case where n becomes infinitely large. Then, both an and an plus 1 must have their limit value. So if we let limit of an as alpha, we have alpha equals 2 over 3 minus alpha, which gives alpha squared minus 3 alpha plus 2 equals 0. So we have alpha equals 1 or alpha equals 2. Here we already encounter a problem that we cannot determine which one of these two are the correct value of the limit. Moreover, using this method in this problem is straight up wrong, because in the process of substituting an and an plus 1 with alpha, we already assume that this sequence actually converges. But it is not stated or already proved that the given sequence actually converges, which means that we cannot simply use this method. Another method of guessing the limit is by using graphs. More specifically, using graphs of y equals 2 over 3 minus x and y equals x. Two graphs intersect at points 1, 1 and 2, 2. Here we can construct something called the cobweb plot. First, it is given that a1 equals 1/2. Therefore, using the graph of y equals 2 over 3 minus x, we know that this y coordinate is a2. And using the graph of y equals x, we know that this x coordinate is a2. Then, by the same process, you can see that this coordinate is a3. So this x-coordinate is also a3. And if we keep doing this, you can easily see that you approach the intersection point 1, 1, meaning that sequence an converges to 1. This use of graphs is definitely a useful tool to guess the limit, but since it inherently relies on drawings, it is still not a strict proof that the limit actually converges to 1. The mathematically rigorous proof is as follows. So even though these two methods are at best guessing, these guesses do provide some useful starting points to rigorously prove the limit. First, it seems that the value of the limit must be 1. So let's keep this value in mind. Second, especially from the graph method, it seems that an is greater than 0 and less than 1 for all natural numbers n. So let us start by mathematically proving this second guess. So in the first step, we prove that an is greater than 0 and less than 1 for all natural numbers n. Here we use mathematical induction. The base case for n equals 1 is obvious since a1 is given as 1/2. Now assume that ak is greater than 0 and less than 1 for some natural number k. Then, from this assumption, we have 3 minus ak is less than 3 and greater than 2. So we have 2 divided by 3 minus ak is greater than 2 over 3 and less than 1. And since this is ak plus 1 by the recurrence relation, we have ak plus 1 is greater than 2 over 3 and less than 1. Hence, the inequality ak plus 1 being greater than 0 and less than 1 also holds. Therefore, by mathematical induction, an is greater than 0 and less than 1 for all natural numbers n. The next step comes from one of our guesses that the value of the limit must be 1. Therefore, we will try to obtain some kind of inequality, including 1 minus an and 1 minus an plus 1. Here, from the recurrence relation, 1 minus an plus 1 equals 1 minus 2 divided by 3 minus an. So we have 1 minus an divided by 3 minus an. So here we have 1 minus an plus 1 and 1 minus an. Here we have already proved that an is greater than 0 and less than 1 for all natural numbers n. Therefore, 3 minus an must be greater than 2, so 1 over 3 minus an must be less than 1 over 2. So using this inequality, 1 minus an plus 1 is less than 1 over 2 times 1 minus an. And this inequality is true for all natural numbers n. The final step is to apply the squeeze theorem using the previously proved inequality. So using this inequality, 1 minus an is less than 1/2 times 1 minus an minus 1. And if we apply the inequality again, we have less than 1/2 squared times 1 minus n minus 2. And we can go on and on until we have less than 1/2 to the power of n minus 1 times 1 minus the first term a1. Here, combined with an being greater than 0 and less than 1, we have 1 minus an is greater than 0 and less than this rightmost expression. Now notice that as n goes infinity, this part right here approaches 0 because of this geometric progression with the common ratio of 1/2. Therefore, by the squeeze theorem, the limit of 1 minus an as n approaches infinity is 0. Here we want to find the limit value of an. And the mathematically strict way to do that is by letting this 1 minus an as bn. Then we have limit of bn as n approaches infinity is 0. Also, we have an equals 1 minus bn. Therefore, the limit of an is limit of 1 minus bn, and we can split the limit like this because we know that both limits converge. So we have 1 minus 0, which gives 1. And that was all for today's video. Thank you for watching, and I will see you in another video.